Hi, I'm Chem's best friend. If you need chemistry help, the information how to contact me is on the bottom of your screen. So welcome back. In a previous video, we talked about trends of periodic table, and we went over the trend of atomic size and ionic size. And in this video, we will tackle the last three trends: ionization energy, electron affinity, and electronegativity. So are you ready? Let's go to my screen. So let's just jump right in and say, what is ionization energy? And that is energy required to remove an electron from an atom. And if it's not specified, we always will talk about first ionization energy. And that is energy required to remove the first electron. If you are talking about second ionization energy, that's energy required to remove second electron. And if you're talking about third ionization energy, well, you know what's coming up. It's energy required to remove third electron, and it can keep going until you remove all the electrons from an atom. If we look at the trend, and this is all just first ionization energy numbers of some periodic table, and again, transition metals are skipped, are removed, and you will see in a minute why. There is a definite trend emerging. And that means if you go down a column, right, down a family, the ionization energy decreases, meaning it gets easier. It takes less and less energy to remove an electron, meaning it's easier to remove an electron as you go down. But if you go across a period, you can see that the numbers generally increase. So it gets harder to remove electron as you go across a period. Let's explain why. Oh, and also if you take all of these numbers and actually graph them, right, you will see, again, here it is. If you go across a period, the numbers generally increase. There is some little exceptions, and we will actually go through them. They increase. And now you can see the blue. These are your transition metals. Do you see why it's left out? There is very little variation between them. So do not pick transition metals to explain trends of periodic table. But as you go across the period, generally the numbers increase. And if you go down the column, so here is our lithium, sodium, potassium. If you go down the column, the numbers slightly decrease, right? So they go down. And if you look at this period, you can see the green, where green are your inner transition metals, and there's even less variation between them. So you have inner transition metals, and then the red and yellow are your representative elements. So there's definite patterns emerging. And let's explain why. So again, I'm choosing three elements. I'm trying to explain ionization energy trend left and right and up and down. And I'm picking some elements which are just really nice to pick. So representative elements, sodium, magnesium, potassium. So one more time, let's write our electron configuration. So 1s2, 2s2, 2p6. Oops, this is doesn't look good. 2p6, 3s1, 1s2, 2s2, 2p6, 3s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And I'm going to quickly draw my picture. So sodium, 11 protons, 3 energy layers, and I have 2 electrons, 8 electrons, 1 electron. My last electron looking in, E and C, is +1. If you are looking at this video first time and you are saying, what's E and C, what is she doing? I explain all of this slowly in the first part of periodic trends video. So, okay, let's go here. Magnesium, we have, different color. Magnesium, we have 12 protons in the nucleus, and we have 3 energy layers, and we have 2 electrons, 8 electrons, and last 2 electrons, and the last electron looking in, E and C, is +2. So let's think about this one more time. It's the same number of energy layers, which is 3. However, magnesium has higher ENC. Higher ENC is more attraction. If it's more attraction, if these electrons are more attracted to the nucleus, they are also closer, and it's harder to remove them. So the higher the ENC, the harder it is to remove electrons because more attraction. So magnesium has higher ionization energy than sodium. And now you can imagine if we go then to aluminum silicon, what's going on? You are adding more and more electrons onto the same energy layer. So your core electrons is not changing. Your number of protons is changing. So what's happening? ENC is growing, right? As you go across the period, here is ENC plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8. ENC is growing, the attraction is growing, the ionization energy is growing. It becomes harder to remove an electron. Now, there are a little bit of exceptions, and we will get to them in a second. But overall, harder to remove an electron. Is that making sense? Let's go quickly to potassium. Let's do potassium. Potassium is 19 protons, and we're going to do our 4 energy layers, and we have 2 electrons, 8 electrons, 8 electrons, and last electron. And then the last electron looking in, so 19 minus 18, ENC is plus 1, and you say, aha, sodium and potassium have same number of ENC. That's right, but potassium has more energy layers. More energy layers means farther away from the nucleus. If it's farther away from the nucleus, it's easier to remove. So that means right here, this is our lowest ionization energy. And magnesium from these 3 has highest ionization energy, first ionization energy. All right, so is this making sense? And you can do this with all the representative elements, and you will see as you go across, ENC is growing, harder to remove. As you go down, energy layers are growing, easier to remove. Okay, so let's go here. So are there any breaks in a trend? Yes, there is. And we can see if you go from beryllium to boron, the numbers actually decrease. And as you go from nitrogen to oxygen, the numbers decrease. Now, this also happens here. If you go magnesium to aluminum, phosphorus and sulfur, this happens less and less if you go from calcium to gallium, right? And then if you go from arsenic to selenium, and then the trend kind of disappears, really, as you go more and more energy layers. So let's explain what's going on. So we are explaining these little things right there, and you can see that the trend becomes less and less pronounced as you keep going. And right here almost equal, and right here the trend doesn't really even happen. So let's explain why, and let's go with. So beryllium and boron. All right, we do our electron configuration, 1s2 and then 2s2, and that's it. And then boron, 1s2, 2s2, 2p1, and we draw our picture. All right, beryllium, 4 protons, and boom, boom, here we go, 2 electrons here, 2 electrons here, the last electron looking in, ENC plus 2. Boron, we have 5 protons in the nucleus, 2 energy layers. We have 2 electrons on the first one and 3 electrons on the last one. It's the last electrons looking in, so 5 minus 2, ENC is plus 3. You say, oh, boron has higher ENC. It should be, with more attraction, harder to remove. But it's not the case, right? Beryllium, the ionization energy is 899, but for boron is 801 kilojoules per mole. So what's going on here? How can we explain it? Well, it all goes back to our electron configuration. Do you remember how we did this? We had our first energy layer, then second, and then there were the p orbitals. So this is my 1s, this is my 2s, and this is my 2p. And then let's do this here. This is my 1s, 2s, and this is 2p, right? So for beryllium, have 1s2, and I have 2s2. That's it. And for boron, I have 1s2, 2s2, and 2p1. Now, remember we had this Hans rule. And Hans rule say maximize a spin. And that means fully filled or half-filled orbitals are extra stable. Aha! So in beryllium, the 1s and 2s are fully filled. This is empty. We have nice stability, right? But for boron, we have this add electron, add man out. So it actually is easier to remove this guy than to break up something that's really stable and happy. So for this reason, boron, Hans rule, boron has a lower ionization energy right here versus beryllium. Okay? Maybe you will see it one more time. And this now goes again on the higher energy levels with magnesium and aluminum. Let's show this one more time with nitrogen and oxygen. So nitrogen, we have 1s2, 2s2, 2p3, and oxygen we have 1s2, 2s2, 2p4. And we draw quickly our, so we have 7 protons, 2 energy layers. Oxygen, we have 8 protons, 2 energy layers. We put our electrons in, 2 electrons, 5 electrons, yes, 2 electrons, 6 electrons. Last electron looking in, ENC is plus 5, what I expect. And the last electron looking in, ENC, where 8 minus 2 is plus 6. This is exactly what I expect. And you say, aha, this is higher ENC, more attraction. Yes, but again, oxygen is actually lower ionization energy than nitrogen. Yes, oxygen, and let's explain why. And it goes back to Hans rule. So we have our 1s2, my 2, and then again 1s, 2s, and then 2p. Let's fill in the electrons. So we have 1, 2, 3, 4, and then up, 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 Hans rule, yes. And then here we have 1, 2, 1, 2, and then up, 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 and I need one more down. And what does Hans rule say? Maximize same spin. That means half-filled or fully filled orbitals are extra stable. And right here, I have half-filled. If it's extra stable, it will be hard to remove this electron because we already have something stable, something nice. Don't mess up a good thing. Whereas here, in oxygen, I do have an add electron. If I remove only this one, I have half-filled orbitals, half-filled p layer. So that will bring me to stability. So for that reason, this electron much easier to remove than this electron. Okay? So Hans rule explains a lot of things. And it keeps going. Now, why does this trend disappear as you go here? And the reason is you're putting so many energy layers, you farther and farther away from the nucleus, that it no longer really matters. Electrons are so far away that they are like, oh, we don't really care. There's more other things going on. Okay, and ionization energy, if you look also a little bit more at second ionization energy and third, you will see that here we go. We're going on a third period, third layer. So if we go from sodium to argon, you will see that, yes, on average, the ionization energy increases. We talked about our exceptions right here. And we know our exceptions. But then, if you go second energy layer, second ionization energy, you can see it again increases, but this number is really high. and you look at third ionization energy, sodium and magnesium will have really high numbers, and then again the numbers will increase. So there is this big jump also. From here, there is a jump. So always removing second electron is harder than the first one. So of course the numbers increase, but it's just that here it's almost 10 times the jump. Big jump. And here again, huge jump. So what's going on? Well, remember, how many valence electrons did sodium have? Sodium has 1 valence electron. So it's easy to remove a 1 electron, but then the second electron, you would be removing core electron. Very hard to remove that. Remember, sodium ion Na+ is 1s2, 2s2, 2p6. You will be removing an electron from the 2p6 region. Yes, from the 2p orbital region. Will be very hard to mess that up. Very hard to do that, because also Hund's rule. So magnesium, the first 2 ionization energies, doable, but then very hard, because you'll be removing core electrons. Okay? Does that make sense? All right. So overall, ionization energy increases this way. Why? Well, I'm going to say it decreases this way. It's easier for me to say this. It decreases this way because you're adding more energy layers. The electrons are farther and farther away from the nucleus. Easier to remove. And then it increases this way as you go across the period. Why? Because ENC increases. ENC increases, attractions increases, harder to remove. All right? Okay. So let's go to electron affinity. Now, chances are this is not going to be spent a long time in class. So atomic size, ionic size, and ionization energy, very important. This one is kind of like almost like a little afterthought, but let's go over it. So electron affinity is energy change. Usually it will be a negative number. Energy will be released, usually, when an electron is added to an isolated gas atom to form a gas ion. So ionization energy, we are removing an electron from an atom. Here, electron affinity, we are adding an electron. We are adding an electron to a neutral atom, and now we are making an ion. Now, you can probably realize, wait a minute, I have metals which don't want electrons to be added. They much rather lose an electron. But non-metals like to gain electrons, yes? And this is what we see. So you can imagine, the more negative the number, the more favorable reaction, right? Because more energy is released, so the more favorable. So negative numbers is, yes, they do want to add electrons. So let's look through here. Do we want to add electrons? So the first column, we have some negative numbers. All right. The second column, alkaline earth metals, actually here we have positive numbers and very small negative numbers. They really don't want electron to be added if you have to force it. Why? Well, if you are removing an electron, if you are adding an electron here, you will be adding it to the S, right? And then you add one more and you will fill that energy layer. Right? You will fill that. But here, if you will be adding one more electron to alkaline earth metals, you will have to put it in a p orbital. They really don't like it. Right? We talked about Hund's rule. So you can see why these numbers actually, yes, from -60 to now positive number, not a good reaction. Here you have many negative numbers, which is very favorable, especially halogens. Of course, they want to add that electron. Now, noble gases, they don't want electron to be added. For them, electron affinity is positive. That means you really have to force it. They don't want to electron added. Why? Because they have S&P filled. They are really good. They don't want it. You will have to add a new energy layer. But halogen, they will get their S&P filled. They like, oh yeah, give me that electron. These guys, they have to add 2 electrons. Great. But these guys, remember what happened to the nitrogen, phosphorus, arsenic, antimony, what's going on? They have the p orbitals have filled, right? They have p3, they have p orbitals have filled. They don't really want to add that 4th electron because it will mess up the nice Hund's rule, have filled. So you can see this is positive number. But overall, as you go here, think about this. ENC is increasing. If ENC increases, there is more attraction. It's easier. Yes, let's add the electron, more favorable. And as you go down, honestly, they don't care. You adding an electron to the farther and farther away from the nucleus, they don't really care. So what happens right here? High ENC, and you would be adding an electron to low energy layers. And this is why these are the highest numbers, right? Especially here, very high ENC, you will be adding an electron to something that's very attractive to the nucleus. And right here will be small energy layers. So, is that making sense? And we just explained the little numbers here. So, overall, electron affinity increases this way. So, a trend very similar to electron affinity is electronegativity. Now, what's the difference between them? Well, electron affinity, you are adding an electron to an isolated atom. You're adding an electron to an isolated atom. All right, electronegativity, you are already talking about atoms in a covalent bond. So they are sharing electrons. And now the question is, how hard an atom will pull an electron in a covalent bond that's being shared. So it's a little bit different numbers, but they come off a little bit from electron affinity. So this one you will really talk about in your biology classes, in biochemistry classes. Oh, biochemistry classes, this will become the most important trend. So this is Linus Pauling. It comes up with this scale, and again, which atoms, which elements had the highest electron affinity right here. So now in a covalent bond, they will still want to pull that electron closer to the nucleus, the shared one. So this is my highest electronegativity. Now remember, the highest 4 electronegativities right here: nitrogen, oxygen, fluorine, chlorine. And the reason is they have, you're pulling electrons to a low energy, close to the nucleus, low energy layers, and again, high ENCs. And you can see that this is the scale. It's a relative scale, but he's like comparing, and these atoms want electrons. Here, not much. They do not, very low. They do not want electrons. So this will help you determine if a molecule is polar or non-polar. But that's another video. So I hope you learned the trends of ionization energy, electron affinity, and electronegativity, and I hope it makes sense. So thanks for watching, and see you next time.